Mhm. Yeah. Is the today's probably the emptiest day so far this quarter. After the midterm. Yeah. People like no more vocab for the next week. Mhm. Okay, so today the plan is to finish up chapter 17, the aldehyde and ketone chapter. And then if we have time at the end, I think we will have time at the end, do a lot of practice rounds on chapter 17. And probably start chapter 18 as well, because there's a few things left for chapter 17. Chapter 18, the alpha carbon, keto tautomerization. Yeah. Okay. Okay. So let's look at the differences between an acetal versus a hemiacetal. An acetal is going to be when we have a carbon attached to two OR groups. So one OR group there, another OR group there. A hemiacetal is when that carbon is attached to one OR group and the other half is attached to an OH group. So you could think of it as like half of the carbon has an OR, the other half has an OH. Hemi, half, acetal. Acetal has two OR groups on that carbon right there. We saw an example of a cyclic acetal, which looks like this here, where the carbon that is the acetal is that carbon there with two ORs, this OR here and that OR there. Right. So now let's go over the reaction of nucleophilic addition of alcohols to aldehydes and ketones. Right. let's look at this example here where let's say we have this aldehyde and we put that through an alcohol like, let's say methanol, CH3OH. We are going to have this acetal here, where if we look at the carbonyl carbon, that carbonyl carbon is going to have two OR groups, right? And assume this is an excess amount, where the OR group comes from the alcohol here. Since I used methanol, a CH3OH, the OR group has to be OCH3. If I used ethanol, the OR group has to be OCH2CH3, right? And this could happen in acidic conditions like H plus, like H2SO4 or H3O plus, or it can happen in basic conditions where the base has to be the OR minus of the alcohol. In this case, since I use methanol, it has to be methoxide. If I use ethanol, it has to be ethoxide, like the OR minus version of the ROH, right? This follows the same pattern of what we did yesterday. We are going to deprotonate the group that you want to stay and protonate the group that you want to leave. Okay, so let's look at acidic conditions because we have two conditions, acidic and basic. Let's say we have that aldehyde that we started with there, and we used methanol here, CH3OH in H2SO4, right? When we have a strong acid, what do you guys think is going to happen here first? Yeah, the oxygen here, which is our most basic atom in this molecule, is going to act as the base and get protonated by the strong acid we have here in the solution. So that oxygen there is going to pick up that proton and kick out that conjugate base to activate that carbonyl, right? Now, this oxygen here with 3 bonds has a positive charge, which makes this carbonyl carbon activated. It has a bigger partial positive charge now because this oxygen really wants to steal its electrons more and take that double bond, right? Once we have that, this weak nucleophile alcohol can now attack this strong activated carbonyl, pop the double bond onto the oxygen to get this here. Wait, I'm gonna leave the hydrogen as invisible now, where we know that this oxygen here attacked that carbon. So that oxygen is going to be there. And that oxygen is attached to a CH3 and a hydrogen here. Okay, now this is the pattern, deprotonate the group you want to stay and protonate the group you want to leave part, right? So which group do you want to deprotonate and which group do you want to protonate? Given this intermediate here, which group do we want to keep and which group do we want to kick out? Okay. And our end product that we are looking for is this acetal here, right? Where this is an acetal because this carbon here has 2 OR groups, OR and OR, right? Since we want this product, do we want to kick out the OH or do we want to kick out this OR group? Yeah, we want to kick out the OH and we want to keep this OR group. But right now, this OR group is a good leaving group because of the positive charge. So we have to make it into a bad leaving group by deprotonating it. And we could do that by using the conjugate base, HSO4 minus. We want to make it into a bad leaving group because we want that group to stay. Right. Now, Do you guys know the name of this functional group here? If this carbon has one OR group and one OH group, half of it is an OR, half of it is an OH. Yeah, hemiacetal. Yeah, right. Uh-huh. Right. Half of it is OR, half of it is OH. So you would stop here. This would be your answer if you had one equivalent or one mole of the alcohol, right? But we have excess. If you see no equivalents or no moles, assume excess amount of the alcohol. We said that we want to get rid of this OH, but right now it's a bad leaving group. To make it into a good leaving group, we have to protonate it using a strong acid, H2SO4, right? Once we protonated it and made that into a good leaving group, we have to drive that good leaving group off by forming a carbonyl between this carbon and this oxygen here. That will kick off that good leaving group that we just formed and give us this carbonyl here, where this oxygen has a methyl group, which is that methyl group there, right? This hydrogen here is this invisible hydrogen there, right? But now we have an activated carbonyl where the second equivalence or the second mole of the alcohol is going to come in, attack that activated carbonyl, and pop that double bond onto the oxygen there, right? That will give us this almost acetal, where the very last step to get the acetal we want is to neutralize it, right? And to neutralize it, we gotta use this conjugate base here. And once we have deprotonated it, we get to the acetal we want, the carbon with the two OR groups. And that was the mechanism for acidic conditions. Now let's go over the mechanism for basic conditions. Right. Let's say that we have the same reactant, this aldehyde here, but this time the reagents are going to be CH3ONA. Right. Whenever you see an Na charge or a K, right, that is always going to be positively charged. And whatever is attached to this Na or K is always negatively charged, which this oxygen here is negatively charged, right? This OR minus is a strong nucleophile, which is strong enough to just directly attack the carbonyl carbon and pop the double bond onto the oxygen right there. We do not have to activate the carbonyl by protonating it because this OR minus here is strong enough to attack that carbonyl, right? Once that happens, we get this here, the O minus and the OCH3, right? Well, the next step is to neutralize that O minus by protonating it. But we don't have H2SO4 or H3O plus. Our proton source is this ROH here that we have on the arrow, right? Because we are not in acidic conditions anymore. We don't have H2SO4 or H3O plus. We have neutral alcohol, which will serve as our proton source. Right. If we had one EQ or one mole of the alcohol, we stop here at the hemiacetal, where this carbon has an OR group and an OH group. Right. Hemiacetal stop at one equivalence or mole of the nucleophile. Right. So now we want this OH group to leave, but right now it's a bad leaving group. To make it into a good leaving group, we have to protonate it again. using the alcohol and get to that good leaving group here, OCH3. Once we form that good leaving group, we drive that good leaving group off by forming a carbonyl between this carbon and oxygen and kicking that group out to get us this carbonyl here, where a second equivalence of base, the CH3O minus, is going to come in, attack that carbon, pop the double bond to the oxygen, and get us our final answer here. Right. OCH3, OCH3. Where this final answer here is our acetal, where this carbon here is attached to two OR groups, OR and OR. Right. In acidic and basic conditions, we get to the same product. The mechanism is just a little bit different. Yeah. Oh, right. The hydrogen group that's attached to the aldehyde here is still there. I just made it invisible. Yeah, but it's still there. Yeah. If you include it in the mechanism, it's not wrong. Okay. Now let's go over imine and enamine. Do you guys remember up to one point he stopped that lecture today? Like what topic he went over today? Oh, nucleophilic addition, like to form acetal, hemiacetal, or
Just like going over like the basic mechanism of nucleophilic.
oh, nucleophilic.
You mentioned like that.
The alkyne chapter. Yeah. That's why he's bringing it back up. I see. Midterm, yeah. Okay, it's good. So an imine is going to be a carbon double bonded to a nitrogen. A carbonyl was a carbon double bonded to an oxygen. An imine is a carbon double bonded to nitrogen. And this nitrogen could have a hydrogen there. It could have an R group there, right? Because for a nitrogen to be neutral, it only wants 3 bonds. It already has its 2 bonds to the carbon there. It only needs 1 more bond to something else, either a hydrogen or an R group to be neutral. Right. If it has like 2 more bonds, like let's say NH2, that nitrogen would have what kind of charge if it has 4 bonds? No lone pairs of electrons, just 4 bonds. Yeah, plus charge, positive charge, right? Nitrogen with 4 bonds, no lone pairs, plus charge. Because nitrogen is on the 5th column, it wants 5 electrons to itself. But right now it has 1, 2, 3, 4 electrons to itself. 5 minus 4, 1 plus 1. Right. This here is called an iminium ion. Iminium ion. Because it is positively charged. It doesn't have to be 2 hydrogens. It could be 2 R groups, or it could be 1 R group, 1 hydrogen. Right. An enamine is similar to an enol, where we have an alkene next to an amine, like that. Right. It could be like this as well. Or it could be like that, where the amine could have like, it could be a primary amine, secondary amine, or tertiary amine. Right. Where the enamine is an alkene next to an amine there. Okay. Now let's learn how to form imines from aldehydes or ketones. Right. Let's look at imine first. Right. The reagent that you need to form imines is either ammonia, NH3, or a primary amine. If you have a secondary amine, that would not create an imine. That will create an enamine. But let's go over the mechanism of this first. Let's say we have this ketone here. And we put that through, let's say, this amine here. Right? And we have H2SO4. We are going to get this product here, this imine here. Oh, whoa, not benzene. Right. Okay. Where that nitrogen with its R group is that same exact R group of the amine we had in the reagent. Okay, let's go over this mechanism. Okay. In the previous reactions, we always activated the carbonyl by protonating it. But in this case here, we have two competing bases, the oxygen and the nitrogen. Which atom is a stronger base? Yeah, so we want to protonate the oxygen, but we can't because this nitrogen here is a stronger base, right? The reason why is because it is less electronegative. And if it is less electronegative, it is more willing to give up its electrons and attack. Oxygen is more electronegative than nitrogen, so it's less willing to give up electrons and attack. So the stronger base here is nitrogen because less electronegative. Right. So we're gonna use this nitrogen amine to get protonated by the strong acid. And then get this protonated positive charged nitrogen there. And then from this point here, this will serve as our acid source now for the carbonyl. We bring in the carbonyl, where this carbonyl oxygen here is going to just get protonated to get our activated carbonyl we want, the protonated carbonyl here, right? We'll know for sure, like if Pascal allows you to get to this point directly, what he goes over the mechanism, because you could just say the H2SO4 protonates this directly, which Helix allows that, but Neseri doesn't allow that. Neseri wants you to do this amine first, and then use this as a proton source for the ketone. But we'll see what Pascal wants when he goes over this mechanism in class. Right. But now, once we have this activated carbonyl, this amine here can now attack that activated carbonyl and pop that double bond onto the oxygen there, right? That is going to give us this OH, nitrogen, with its R group, and its two hydrogens still attached to that nitrogen there, right? That nitrogen with 4 bonds, like we said earlier, will have a positive charge. Now, at this point here, we do the exact same pattern. Deprotonate the group you want to stay, protonate the group you want to leave. Since we're trying to form the imine group, right? Which group do you want to keep here? The OH or that weird nitrogen group on it? Wait, the OH, do we want to kick that out or keep it? If we want to form this imine here. Yeah, kick it out, right. So we want this group here to stay, but right now it's a good leaving group. To make it into a bad leaving group, we deprotonate it using the conjugate base we formed earlier here. That gives us this OH here, nitrogen there. And now this amine is neutral, which is good because we want it to stay. The OH is the group we want to kick out because we don't have any oxygen in this product at all. We want to get rid of that oxygen. To do that, we have to convert that bad leaving group into a good leaving group by protonating it with a strong acid here. Right? That will convert that bad leaving group into a good leaving group. This oxonium ion here. Right. Once we form that good leaving group, we drive that good leaving group off by forming this iminium bond, and kicking out that leaving group there. Right, water leaves. Okay, we're almost at the final imine here. Right, there's just one last step, which is just to neutralize and deprotonate that nitrogen using the conjugate base here. Right, and that gives us our imine bond that we wanted here. Yeah. This is a reversible reaction where if he asks you to draw the mechanism of, let's say, that imine back to a carbonyl using water and acid, H2SO4, try this mechanism for a few minutes and then I will go over this, right? It's the same exact like concept and steps on the previous mechanism we just did, but just different nucleophiles and electrophiles. Yeah.
How does it hydrate connected to the nitrogen?
Oh, right. This hydrogen here attached to the nitrogen is still attached to the nitrogen right before the final step, where the final step is grabbing that hydrogen to deprotonate the nitrogen and make it neutral. Because right now it's positively charged. To neutralize it, we deprotonate it to give our final answer here, right?
Is there a reason the molecule with a double bond and keep the hydrogen?
Oh, like this double bond here?
Yeah.
Let's see. Think of it as like we have excess amount of amine here. Once we put that through this carbonyl with acid, we get up to this point here, right? Where this, as well as the water that left, this water came from the carbonyl here, right? Because in the mechanism, we saw that that water left in the mechanism. This increased entropy in the reaction because we had one molecule before, but now we have two molecules in the products. This is favored, which is why we want to stay in this form here. If the hydrogen was still there, that would make this whole molecule here less stable. Right? To make it more stable, we want to make it neutral by deprotonating it.
Oh, no.
Uh-huh.
Well, what if the nitrogen just had like a single bond connected to the cyclohexane,
Uh-huh.
and then it's another single bond connected to the hydrogen?
Oh, like, let's see. Single bond like that, and then single bond to nitrogen, and then amine like that. Right. So this one here, let's see. What's can that happen? Oh, which is this point here.
Yeah.
Right. Once we create this good leaving group, if we just kick out the leaving group by itself, we are going to have that nitrogen that you just talked about, the single bond with the carbon and the hydrogen attached to it still, right? But this carbon here will have a positive charge, right? Which is not good because that carbon there does not have the octet role. No.
Could you protonate that?
Oh, no. We can't protonate this carbon because to protonate things, it has to have a pair of electrons to attack a proton.
Oh,
right.
Just
Yeah, no electrons. Yeah.
So you need to give electrons from the hydrogen instead of giving it the actual hydrogen.
To give this an extra bond, the extra bond comes from this nitrogen's lone pair of electrons right there. The hydrogen here is still attached to this nitrogen there, right? Once we have done that, we get to this point here, right? I just drew it as a concerted step here where that lone pair of electrons makes a double bond with that carbon and nitrogen at the same time as that leaving group leaves. But you could have said that the leaving group leaves by itself first, like an SN1 manner, to form this carbocation here. And then the lone pair of nitrogens gives it an extra bond to give this structure here, right? Yeah. Yeah, these are good conceptual questions, because it helps you memorize the mechanisms better down the road, right? This cannot be a product because this carbon here is not neutral. It will have a positive charge in the mechanism. Yeah. Right. Okay, now try this mechanism here, converting an imine into carbonyl using water and acid. Right. In this case, the first step, we don't have to worry about that acid base thing because nitrogen here is going to be the one that's going to get protonated first to make the good leaving group.
Yeah, I think that's it. Wait, did you use that? Yeah. Oh, I think that's different than this one.
Okay. What was the first step that you guys tried doing first here? Yeah, protonate the amine nitrogen to activate that, right? Once we protonated this nitrogen here and give it a positive charge, what is the next step? Yeah, attack the carbon with water, which is going to also pop this iminium ion bond onto the nitrogen there and neutralize that, right? And once we have done that, we get this intermediate here. where this nitrogen is neutral, this oxygen is positively charged because it has 3 bonds. Whenever you get to this point here with the pattern, you deprotonate the group you want to stay and protonate the group you want to leave. This is specifically called a tetrahedral intermediate. So that might show up on the vocab for the next exam, where this tetrahedral intermediate means that this carbon here is in a tetrahedral shape with bonds to electronegative atoms, where in this case specifically, this carbon is bonded to an electronegative nitrogen and an electronegative oxygen, right? That's why these tetrahedral intermediates are unstable, because that carbon there, its electrons are being pulled by that nitrogen and this oxygen here, making that carbon very, very positive and unstable. Right. So because it's very unstable, this is going to be a temporary intermediate where we deprotonate the group that we want to keep, and then we protonate group we want to stay. Okay, so if we want to get back to the carbonyl here with the oxygen, which group do we want to keep? Yeah, the water. So we have to deprotonate that using the conjugate base. And that becomes OH. And this amine here is neutral. There. Okay. We want this amine group to leave because there's no nitrogens in the product at all. But right now, it's a bad leaving group. To make it into a good leaving group, we have to protonate it and give it a positive charge, good leaving group. Right. That nitrogen there with 4 bonds now has a positive charge, where this whole thing here is the good leaving group. We drive that good leaving group off by forming a carbonyl bond and then kicking that amine out.
So does the hydrogen from the sulfuric acid go to the amine group?
Yes, the hydrogen here of the sulfuric acid goes to this amine group here, because this nitrogen is grabbing the hydrogen with its lone pairs.
And can it be like direct, can the nitrogen from the amine group just directly grab the hydrogen from the like can it just, like,
from this point here?
Yeah.
Oh, this point here, this nitrogen has no pairs of electrons. It just has 4 bonds.
Oh no, actually no, the step.
Oh, this one here?
Yeah. Like instead of like going through the step.
Like doing that first and then deprotonating this water here.
Can you just like grab it like directly?
Yes, it can do that. It can grab the hydrogen from the H2SO4 directly, but that would introduce a positive charge on that nitrogen as well when it grabs that hydrogen, right? But there's a positive charge nearby already, so that makes it unstable. We want to reduce the amount of charges, so that's why we want to get rid of this charge first and then protonate that.
Okay, so that's good.
Yeah. Nice. Right. So once we have like neutralized this positive charge that is in the water, every single molecule or an atom here is neutral. And then we could protonate this nitrogen to give that a positive charge. And then once that positive charge is there, that's a good leaving group that could get kicked out by reforming this carbonyl here. And then this amine here gets reformed. And the conjugate base just neutralizes that carbonyl, oxygen, to give us the desired product we want, the carbonyl. Nice. Okay, so let's go over forming enamines now. That was the forward and reverse mechanism of imine, like going forward to the imine and then going backward to the carbonyl mechanism. Forming enamine. Like these 2 chapters here, there's a lot of reactions and mechanisms because of the forward, reverse mechanism, acidic and basic conditions as well. But it follows the same pattern. Deprotonate the group you want to stay, proteinated the group you want to leave, just different nucleophiles and conditions, right? Let's say now we want to make an enamine. This will come from a secondary amine, like R2NH, right? So let's say we have the same carbonyl, that cyclohexane with that ketone in the middle, but this time our reagent is diethylamine, a secondary amine, acidic conditions. Right. We are going to form this enamine here, this alkene next to that amine right there. Right. This whole thing is the enamine. Let me write that. Enamine. Okay. Let's go over the mechanism. Let's see. We know that we want to activate this carbonyl for this amine to attack, but the nitrogen is more basic than the oxygen. So that's the one that's going to get protonated first, which will serve as our proton source for that carbonyl oxygen. Now, this carbonyl oxygen here is going to grab that hydrogen of the positively charged amine to get activated and give us this better electrophile here. So this is the similar like mechanism, same steps as we did earlier. Once we have this activated carbonyl, we bring in the amine to attack that carbonyl carbon, pop the double bond onto the oxygen, get us this tetrahedral intermediate. Same thing so far, same process. Right. Now, once we get to this tetrahedral intermediate, we want to keep this group with the nitrogen. So we want to deprotonate that group using the conjugate base. Right. Once we deprotonated that group becomes neutral and a bad leaving group, which is good because we want that group to stay. We want the alcohol group to leave, but right now that alcohol group is a bad leaving group. To turn that into a good leaving group, we protonate it. Right. Good leaving group, oxonium ion, that amine still there. Drive that good leaving group off by forming that iminium ion and kicking that water out. Yeah, everything is the same so far as we did in the last example, but now this is where it is different. Because this nitrogen here with 4 bonds has a positive charge. In the last mechanism, we neutralize that positive charge by deprotonating that nitrogen. But we see in this example here, there are no hydrogens to deprotonate on that nitrogen, so we can't neutralize it there. Can you guys think of any other way where this can become neutral?
Oh, can we delete the electrons from the double bond?
Yeah. Like the electrons of this double bond onto that nitrogen.
Yeah.
Right. And let's say that happens. Let's draw the resonance form like that. Yeah, that's right. That's what we want to do. But now, where would the positive charge be at this point here? The nitrogen has a lone pair of electrons now, which came from the bond, but another atom gains the positive charge. Yeah, which is this carbon here, right? So now we want to, like, that's right. This nitrogen here will get neutralized by that bond. But let me redraw this. We also want to like keep that carbon neutral. So think of this as an elimination step, like an E2 reaction, right? Where the base, like HSO4 minus, is going to come in, grab this beta hydrogen, form a double bond here, and then pop this double bond onto the nitrogen there. This nitrogen here will gain that lone pair of electrons by this bond here, right? Well, this is like an E2 like mechanism. The base grabs the beta hydrogen, forms a double bond, and then kicks that leaving group off. But it doesn't fully leave because this is a double bond, not a single bond. That double bond would just become a single bond. And that creates our enamine. Here, like that, where this nitrogen is now neutral with the pair of electrons that it gained from that bond. The carbon is also neutral because it still has its 4 bonds, right? You could have also drawn that like same exact step here, where this base would grab that hydrogen and form a double bond there, right? That will just give you that same exact thing as well. But to save time, you don't have to draw this resonance structure. Once you get to this point, you can do the E2 like mechanism there. Yeah, okay, nice. Now let's do the reverse mechanism, which is a little bit more tricky. Let's say we have that enamine, and we want to go backwards to the carbonyl with water and acid. Right. Okay. Now the thing here, the first step, nitrogen is not going to get protonated. The thing that's going to get protonated is this carbon right here, right? Because I'm just going to draw out the resonance structure of that to show you why that carbon is the nucleophile, the one that attacks. These are resonance structures of each other, where we see that this carbon here of that double bond has a full negative charge, making that the stronger nucleophile, right? So when we draw this whole mechanism, do not protonate the nitrogen of the enamine, right? Reform the imine bond and then use this carbon to get protonated and give you this here, that iminium ion there, right? At this point, think of that as an activated carbonyl where the water just attacks, and we do the whole like same exact mechanism to get to this carbonyl here. So attack that, pop that double bond to the nitrogen, form the tetrahedral intermediate where we deprotonate the group we want to stay, protonate the group we want to leave. We want the oxygen to stay because we have an oxygen in the product, so we want this water to stay. We deprotonate that group to turn that group into a bad leaving group. Right. We want this nitrogen group to leave. To turn this bad leaving group into a good leaving group, we protonate it. Right. Now, once we have formed our good leaving group here, we are going to reform that carbonyl and then kick out that leaving group. That gives us to our almost neutral carbonyl, right? Where the final step is to neutralize that carbonyl using the conjugate base and reform our acid catalyst. Yeah. Yeah. Similar mechanism type, different nucleophile, different electrophile. Okay. Let's see. 1, 2, 3. 3 more reactions left for chapter 17. Okay. Wolff-Kishner reduction. Do you guys want to, like, once we finish chapter 17, just do practice problems and then leave chapter 18 for next week? So then, like, it's not overwhelming. Yeah. Let's just focus on practice problems after we finish chapter 17. No, it's going too fast.
Didn't even call it like many of like the reaction state.
Oh yeah, like the acetal, hemiacetal, imine, enamine, Kushner reduction. Okay, so this is going to be a reduction reaction. So let's say we have a ketone where that carbonyl is in between two different types of R groups. You're going to see these reagents here. There's multiple forms to see it. NH2, NH2, or N2H4. That's just the exact same thing. It's just like different representation. Or H2N, NH2. Like all of these three reagents here are the exact same. They're just different representations of each other. You will see that with sodium hydroxide, water, and heat. Base, water, and heat. What this does is that it will completely reduce this carbonyl down. It will get rid of that carbonyl, right? And give that carbon two hydrogens like that. This is a reduction reaction. Yeah. Yes, H2PDC, but in this reaction here, this does not have to be benzylic carbonyl. Right, but that's a good like correlation. H2PDC will reduce that carbonyl if it is benzylic. But if the carbonyl was not benzylic, H2PDC would not reduce that carbonyl. If this carbonyl here was like in between like random R groups like ethyl and methyl, let's say for example, this reducing agent here will cleave off that carbonyl and reduce that carbonyl. Right. So think of this as a stronger reducing agent than H2PDC. Right. Yeah. Yes, this will also work for benzylic carbonyls as well. Yeah. So if you see a benzene there, you can also use that as well. But that is overreactive because let's say we have a benzene like this, and you have a carbonyl there and carbonyl here. And then in synthesis, let's say you wanted to get to this point here, and we want to maintain that carbonyl, right? We cannot do N2H4 NaOH water and heat because that will give us this product instead, where it cleaves both carbonyls down. If we just wanted to cleave the benzylic one, then we could use H2PDC, like you said, or Clementon reduction, zinc, mercury, HCl. This is a stronger one. It overreacts, like Jones or what's the other one? LiH4, lithium aluminum hydride. Yeah, the mechanism is a beast. There's two steps for this mechanism. Okay, let's see. Okay. Let's separate this mechanism into two steps, two substeps. The first one, let's say that's the formation of an imine. And this imine is going to be specific. It's going to be hydrazone, which I'm going to show in the mechanism when we get to there. The second step of this mechanism is going to be reduction of that imine. Reduction of imine or hydrazone in this case. Okay. Let's bring in that ketone between the two R groups. Okay, so here's the first step here. And now let's bring in the NH2, NH2. One of the pairs of electrons on nitrogen is going to attack that carbonyl carbon and pop the double bond onto the oxygen there, right? When that happens, we are going to get this tetrahedral intermediate here. The reason why we do not have to activate this carbonyl to make it into better electrophile is because think of this as a strong nucleophile. This strong nucleophile is able to attack the carbonyl right away without it being activated or protonated. Right. So when that happens, we are going to get this intermediate here, where the oxygen has a negative charge. This nitrogen is bonded to that hydrogen, this hydrogen, and H2 with a positive charge. Because that nitrogen there has 4 bonds. Right? 1 bond to the hydrogen, 1 bond to that nitrogen, 1 bond to that hydrogen, and 1 bond to that carbon. Right? Now, the next step is to use water as a proton source to protonate that O minus, to convert that into an alcohol, neutral alcohol. Right? Okay. The next step here is to use the OH minus base that was just formed to deprotonate the nitrogen and make it neutral. Get rid of that positive charge. Okay, now we have a neutral tetrahedral intermediate, right? The next step here is to deprotonate this nitrogen again and give that a negative charge. So I'm going to redraw this NH2 like this because that nitrogen is actually bonded to that one hydrogen and this NH2 here. We're going to bring in another base hydroxide ion to deprotonate that nitrogen and give that nitrogen a negative charge. Right. Where we have this negatively charged nitrogen NH2. Right. At this point here, we're going to form an imine bond and then kick out this leaving group here. You are used to seeing this OH as a bad leaving group, but this leaving group here is able to leave because of the basic conditions that it's surrounded in. Like there's a lot of hydroxide ions already. And also you have heat. You have enough energy to push that leaving group off. Basic conditions and heat, right? So this did not have to be OH2 plus. That bad leaving group is just able to leave by itself, not by itself, but able to leave after forming this imine bond and drive that leaving group off because of the basic conditions floating around. Like we have other hydroxide ions supporting this hydroxide ion as it leaves. And also heat to give it enough energy to do that unfavorable leaving group. Right. Oh no. Shoot. Oh, wait, what happened? Hmm. Okay, there we go. Okay. That forms this amine here. And then the hydroxide ion that left, but there's a lot of them around in solution. because we're on basic conditions. This imine here does not have an R group. It has a amine group. When you see that kind of imine, this is specifically called a hydrazone. Right? And that's the end of the first step. Once we formed this hydrazone here. Now let's do the second step. Reduce that hydrazone into hydrogens. Number 2. Okay. Draw in that hydrazone that we just formed. This. Right. I'm drawing out all the bonds here now because this nitrogen is bonded to this NH2, which is this NH2 here. Right. The first step is to deprotonate this nitrogen with the hydrogen and give this nitrogen here a negative charge. Once that happens, we get this negative charge there, hydrogen here. Okay. Okay. So from here, we use that negative charge to make a double bond between this nitrogen and nitrogen here. Because our goal here now is to make the best leaving group, like one of the best leaving groups in OChem, N2 gas, nitrogen gas, where there's a triple bond between the two nitrogens there, right? So right now they have one single bond between them. This step here is going to form the double bond between them. When we do that, we're going to move this double bond to that carbon, which is going to give that carbon a negative charge. Right. Once you have that negative charge, that's just going to get protonated by water because that's our best proton source in this basic conditions. We don't have H2SO4, we don't have H3O plus because we are not in acidic conditions. Right. Once we have protonated that, we get this group here. Right. Where this nitrogen here still has a hydrogen that is acidic for this hydroxide ion to deprotonate and give that nitrogen there a negative charge. We could just like speed up the mechanism here by just making a triple bond between that nitrogen and nitrogen right away, and then giving this carbon here a negative charge. So the leaving group will leave as N2 gas, where a triple bond is going to form between those two nitrogens there. But let me just do this step by step for now to like make it more clear on what's going on. When this hydroxide ion is deprotonating that nitrogen, this nitrogen will gain a negative charge. So let's draw that there. Right. That nitrogen with the negative charge is going to form a triple bond between that nitrogen, and then give that carbon there a negative charge. Right. And now this is going to be the irreversible step here because the best leaving group leaves the nitrogen gas, the N triple bond N, which is this point here. Right. And then we are going to have a negative charge on that carbon, which the very last step is to protonate it using water to give us our reduced carbonyl. Right. Long mechanism.
Professors generally test the mechanism.
I haven't seen this mechanism been tested before. It's mostly the chapter 18 mechanisms that are tested. Those are the big ones, like the aldol condensation, Michael addition, Robinson annihilation. Those mechanisms are more commonly tested than this Wolff-Kishner stuff. Right. This Wolff-Kishner stuff is more for predicted product and synthesis. But I just went over this just in case. Yeah. There's 2 steps for this mechanism. forming the hydrazone imine bond, and then reducing that imine hydrazone to the alkane. Okay. Yeah.
That last step, where's like the second hydrogen?
Oh, right. So it gained this hydrogen from water, and let's say that hydrogen is here. The other hydrogen is going to come from here, right? Like once we have this point there with the imine bond, this nitrogen with the negative charge makes a double bond between the two nitrogens, and then this double bond between carbon and nitrogen gives a pair of electrons to that carbon, and then that carbon gets a negative charge, which gets protonated by some water. But the goal here is like to convert this single bonded nitrogen all the way to the triple bond nitrogen, and then make it leave and remove that whole thing away from the alkane. Yes. Okay. Two more reactions for this chapter. Let's go over the Wittig reaction. Okay, these two are the weird ones. They're short and fast, but weird and funky. Wittig reaction. Okay. So, let's say we have this ketone here, acetone. And the reagent you're going to see is something like this. If you see phosphorus with three phenyl groups attached to it. And we could abbreviate phenyl as pH here, phenyl, three phenyl groups. Right. What this reaction will do is that it is going to combine this carbonyl carbon and this carbon of the phosphorus together and make an alkene. Right. So let me highlight this as yellow and highlight this as blue. What we are going to get is that alkene right there, where this carbonyl, that carbon there is blue, let's say, and this carbon here is pink. This is the yellow highlighted region. This is the blue highlighted region, right? We're basically merging that oxygen and phosphorus together and getting rid of them and making an alkene, right? Where the alkene comes from that merge right there. Okay. Let's go over the mechanism of this here. Okay. I'm going to draw out the phosphorus with the three phenyl groups out and draw its resonance structure. The double bond is going to give that carbon there a lone pair of electrons. Right. That makes this phosphorus positive charge, this carbon here negatively charged. Right. Now, this negatively charged carbon here is going to be the nucleophile. Let's bring in the carbonyl now. The electrophile is going to be that carbonyl carbon right there because that's partially positive. This nucleophile here will attack the electrophile and pop the double bond onto the oxygen right there. Right? What charge would the oxygen have when I pop the double bond to the oxygen? Not a trick question. Negative charge, right? Where that negative charge is attracted to the positive charge, phosphorus, right? So the way we draw this is very important because we are going to draw it in a way where the phosphorus with its three phenyl groups is going to be right next to the oxygen there, right? Because positive and negative charges are attracted. When we draw it like that, let's say this is the star atom here. Star atom there. This is the new bond between the star and dot atom here, right? Because the dot atom was at this thing there, right? That dot atom is attached to two methyl groups, so I'm going to draw those two methyl groups there. And the star atom is also attached to two methyl groups there. Okay. So this oxygen minus here is going to attack that phosphorus and give us this box-looking structure here between the phosphorus and the oxygen there. The phosphorus still has its three phenyl groups. And now this is the last step, which is kind of weird. It's like an electrocyclic reaction where this oxygen phosphorus bond is very strong. It wants to leave. It wants to create another bond. So this bond here is going to make a double bond between that oxygen and phosphorus. And then this bond here is going to make a double bond there to give us that alkene and this phosphine there. The oxygen double bonded to the phosphorus. That's just a side product. Side product. Right. But notice how like we formed a double bond between the carbonyl carbon and the carbon that was double bonded to the phosphorus. They just merge to each other. The mechanism was like short, but kind of weird because the arrows are kind of weird at the last step. Yeah. Okay. Now, this is important because the alkene that you're going to form, there's two scenarios. Mostly the Z alkene is major, and I'll show you an example of that. Like, let's say we have and you on the exam, you might see, wait, actually, never mind. I was gonna say you might see it like this negative charge pH3 positive charge. That is the same thing as this right here, right? They're just resonance forms of each other, but you're most likely gonna see it in this form here, the neutral form, because it is more stable. But because we know this carbon here has a negative charge, that carbon there is the nucleophile. Right? If we have that phosphine reacting with, let's say, this asymmetrical ketone here, our major product is going to be this Z isomer here, right? This is Z because if we make a line through the double bond, the two bulkiest groups are on the same side, right? And the reason why the Z alkene is more favored in this reaction is because if we do the whole mechanism, like we know this carbon here is the nucleophile, attack that, pop that double bond to the oxygen, we're gonna get something like this. Phosphorus, pH3 positive, O minus. Right, where to decrease steric hindrance, right? We want the bulky group facing away from the O minus. We want the bulky group facing away from the positive charge here. Right. So when that happens, we see that the two bulkiest groups here are on the same side. So when we do this whole reaction, when the O minus attacks the phosphorus, we're gonna get this box here. And do the weird mechanism step to form that phosphine bond and that double bond right there, which gives us that Z alkene there, where the bulky groups are going to be on the same side of each other, right? So that's why the Z alkene is favored over the E alkene, right? This is the minor product here. This is minor. So this is the only case where you see the Z alkene is favored over the E alkene, because whenever we did like E2 reactions back in midterm 1, the alkene chapter, we always said the E alkene is major over the Z alkene because of less steric hindrance. But in the Wittig reaction, it's weird. The Z alkene is more favored than the E alkene because of this mechanism here. The bulky groups are facing away at the same side of each other to avoid steric hindrance with these oxygen and phosphorus here. Right. That's the normal case. The weird case, actually, this is crazy because today in lecture, I went over this, like my professor went over this reaction. If your phosphine was, let's see, was it the phosphine or the carbonyl? Let me see. Not conjugated ylide or aldehyde. Conjugated ylide or aldehyde. E. Yeah. Let me make sure. It's conjugated meal give E. Okay. Looks like it's both. So if either your ylide, which is this phosphorus with its 3 phenyl groups, or carbonyl, which is the ketone or aldehyde, is conjugated, meaning that it could do resonance, then your major product is going to be Z, right? If your ylide or carbonyl is non-conjugated, unconjugated, then your major product is E. Where we saw that in this example here, the ylide, this ylide here, was unconjugated. Like this double bond here was not conjugated. There were no other double bonds there. This carbonyl here is also unconjugated because there was no like conjugated system here. Since both ylide and carbonyl was unconjugated, we get the Z alkene. Right? But let's look at an example where we have a conjugated carbonyl. And the carbonyl does have to be a ketone. It could be an aldehyde as well. And also a conjugated ylide. Right? Now, we can see that this carbonyl here can do resonance with the benzene ring here. And this ylide here can do resonance with this ester here. Right? And if it can do resonance, it is considered conjugated, where it's going to follow the same mechanism, but now we are going to form an E alkene instead of a Z alkene. Right? Where let's say this carbonyl carbon is the blue carbon, and this carbon holding the phosphorus is the pink carbon, right? There's going to be a double bond between the blue and pink carbon. And then everything else stays the same. Like that. Where this is the E alkene. Right? And the reason why this prefers to be in the E alkene is because now we want the groups to be near each other. Think of it as like the endo row. You know how we want the electron withdrawing groups, the p orbitals, to be overlapping with each other? This overpowers the steric hindrance rule. It's similar to that, right? We want the p orbitals to overlap with each other to increase p orbital overlap, increase conjugation. Right. Okay. Now, here's an example problem that you might see, or for synthesis as well. If you just have a halo alkane, you can create that into an ylide by putting that through phosphorus and its 3 phenyl groups, right? Think of this phosphorus as nucleophilic. It's going to attack that carbon, kick out the leaving group, SN2 reaction. That gets this, but the phosphorus here will now have a positive charge. We do not have our ylid yet because we want this carbon here to have a negative charge. How can we create a negative charge on this carbon here? Right. To create a negative charge on that carbon, we can deprotonate it. But we said back then that this carbon here with the hydrogen is not that acidic. So we have to use a very strong base. The very strong base that we could use is either N-butyl lithium, or NaH. You could use NaOR as well, but these two are the stronger bases, right? Those bases will deprotonate this carbon to give that carbon a negative charge, right? Now we can see that we have our ylid here, right? Which could just form a double bond there, and we can see the normal version of it, like that. And then from there, you could react it with any carbonyl you want to create, depending on what your synthesis problem is, right? So this is formation of ylid, right? Next. And then from here, depending on the synthesis, you could use any carbonyl you want to make a double bond alkene. Okay, last reaction, the Baeyer-Villiger oxidation reaction of this chapter. Baeyer-Villiger oxidation. So there's this thing called a migratory aptitude list, which is important for this mechanism and reaction. Right. The highest priority is going to be hydrogen, and then tertiary, and then what the heck is this? Let's see. Wait. Secondary. This cyclohexane, and then secondary, which has the same priority as a phenyl group. A phenyl group is, you could think of that as a benzene ring, like this here. Right, and then the lowest priority, oh no, not the lowest priority, and then primary, and then the lowest priority is a methyl group, ACH3. Okay. So let's look at an example problem here. Let's say we have this ketone, and we put that through a peroxy acid, like RCO3H, which you could see that as, let's say, this right here. When you see this peroxy acid and a carbonyl, think of the Baeyer-Villiger reaction. What this reaction would do is insert an oxygen between the carbonyl carbon and the alpha carbon. But in this case here, we have two alpha carbons, a tertiary alpha carbon and a secondary alpha carbon. Based on this migratory aptitude, we see that the tertiary carbon takes priority over the secondary alpha carbon. So that's where the oxygen is going to insert itself between that carbonyl carbon and that carbon right there, right? So this is the answer we get. And be sure to not forget your number of carbon atoms. We have 1, 2, 3, 4, 5, 6, 7 carbon atoms. We have to keep that same amount of carbon atoms here. 1, 2, 3, 4. Wait, 1, 2, 3, 4, 5. And then, oh shoot. Let's say that and that. 1, 2, 3, 4, 5, 6, 7. 7 carbon atoms. So that's the answer for this one, because the oxygen inserted is up between this side, not that side, since tertiary takes priority over secondary. Okay, let's go over the mechanism of this here, which has a weird step to it because a migration step is going to happen. Let's say we have a common ketone in between two R groups like that. Right. I'm going to draw out the peroxy acid like this. This peroxy acid is going to serve as the acid, and then this carbonyl oxygen here is going to get protonated by that peroxy acid. When that happens, we get this protonated carbonyl there, right? And we also have this conjugate base that left, where there's a negative charge on that oxygen there, right? Think of this negative charge conjugate base as the nucleophile now, where this nucleophile is going to do a nucleophilic addition to the carbonyl. It's going to attack this activated carbonyl and pop this double bond onto the oxygen there. And we're going to form that tetrahedral intermediate, right? So I'm going to draw it in this orientation to draw the next step easier, which this next step is going to be weird. Right? Let's say. Right. So this carbon to carbon that got attacked is this carbon right here. The OH is now this OH right here. The O minus that attacked that carbon to carbon is this oxygen with its carboxylate group there. Right. I drew it in this orientation to show the next migration step, where let's number this 1, 2, 3, 4, 5, 6. Right. We see that this partially positive hydrogen and this partially negative hydrogen is around each other because they could do H bonds like that, right? This oxygen here is going to use one of its bonds in the double bond to attack that hydrogen. When that happens, that bond between oxygen and hydrogen is going to make a double bond between that carbon and oxygen there. And then this is the weird step here. This whole R group there, one of that R group, and then this is where you choose like which R group migrates. You choose the R group that is higher in priority in the migratory aptitude list, right? That R group is going to migrate to this oxygen here. And then the bond between this oxygen and oxygen is unstable and make a double bond there, right? So what we get is something like this, where the R group is still here. We get this now oxygen, carbonyl, and then that oxygen is now attached to this R group here that migrated there, right? Now this is the oxygen inserting itself between the carbonyl carbon and the higher priority R group there, right? Where this oxygen here was 1, 2, and this oxygen here was 3, right? The side product is this right here. Where this is oxygen 4, 5, and 6. Right? We made a double bond between 4 and 5, which is that double bond between 4 and 5. There used to be a double bond between 5 and that carbonyl oxygen, but that's now a single bond. And then this oxygen 6 here, grab the hydrogen, which is that hydrogen right there. Grab the hydrogen from atom 1, which is why that atom 1 no longer has a hydrogen. Right. So that's the weird mechanism for Baeyer-Villiger oxidation. I've mostly seen this reaction tested on predicted products, only, or sometimes synthesis. I haven't seen an exam where professors tested the mechanism of this. Yeah. All right. So let me give you guys one more practice problem and then predict where the oxygen will insert itself, depending on this migratory list here. Let me copy and paste that. Oh shoot, here. Okay, let's say we have this benzaldehyde and react it with this peroxy acid. Where would the oxygen insert itself between? Here. So for the right side, we have a hydrogen. The left side, we have a benzene ring. Which one has higher priority, hydrogen or benzene? Depending on this list here. Hydrogen. Hydrogen has the highest priority. So the oxygen is going to insert itself between that carbonyl carbon and this hydrogen here, which gives us this carboxylic acid there. Right. So that's an example problem of that Baeyer-Villiger oxidation. Nice. Okay, so that's all for the major reactions. These last reactions are for lab, but it's pretty quick. They are just tests for aldehydes. Let's say for in lab, you predict that your molecule has an aldehyde. You could either do something called a Fehling's test or Tollens test. Right. These are oxidative chemical tests for aldehydes. Right. So let's look at Fehling's test. Let's say we do have an aldehyde here. The reagents that you will see for that are copper, 2 plus ion, NaOH or KOH, and water. Right. What that would do is create a carboxylate here and copper 2 oxide solid, which you're going to see as a brick red color in lab. Right. If you do not have an aldehyde, like let's say you have a ketone instead, and you try to do Fehling's test on it, no reaction will happen, and you will see no color. It will be colorless. So a positive test for this is if you see a red color, that means that you have an aldehyde in your molecule. If you see no color, then you know that you do not have an aldehyde in your molecule. Nothing happened, no reaction. The other test is Tollens test, which let's use the same thing, aldehyde or ketone. But the reagents are different. Right? Let's get rid of this. Oh my gosh. What you will see is silver plus ammonia and water, right? There are multiple ways to see this, but the most important thing here is silver. You can also see or silver, ammonia, OH, or silver. This is like most likely just gonna be predicted product because you don't need to worry about the mechanism here. Right. Tollens test will convert that into a carboxylate here and create silver um precipitate solid. So this will be clear and colorless. But if you see something precipitating, like a solid, then that's a positive sign that you have an aldehyde. Precipitate, solid. If you try to do the same with a ketone, no aldehyde involved at all, no reaction happens, no precipitate. That means that that's a negative test. No aldehyde present. No precipitate. Right. So these are the tests for your aldehydes, Freiling's test and Tollens test. You also get precipitate for Freiling's test as well, but you also get to see a brick red color. For Tollens test, you just see a precipitate with no color. Okay, that's it for chapter 17. Let's just do problems on this and then do chapter 18 next week.
Thank you.
Yeah, no problem. See ya. Bye. Mhm. Yo, Jin, are you second year or third year?
Oh, second year.
Oh, second year.
Yeah.
What's your major again?
Microbiome?
Oh, microbiome. Let's see. Yeah, you could do the first one. The nucleophile is going to be different though. You know how in the other examples we did alcohols as a nucleophile? In this case, the nucleophile is CN minus. The acid is not H2SO4, the acid here is going to be HCl. So it's not going to form an acetal or a hemiacetal, it's going to form something called cyanohydrin. Similar mechanism, there's different nucleophile and different electrophile. This part B was something we went over today. Part C as well, but this is an intramolecular one, right? Because the alcohol is not outside of this here. The alcohol is within the same molecule as the electrophile. Intramolecular reactions always form the ring. This one we also went over today, and this one as well. So let's do these ones here. The first one is just different nucleophile and acid. And then when you guys are like done with these problems, do you guys want to come up and try writing it on the iPad? You guys are undergrad, you guys are like studying for the final like right after the midterm.
Yeah.
Taking no chances. Have you finished the first part? Yeah.
I don't know how to do it.
Oh, I see, I see. Let's see. Let's go over that first one. Oh, have you tried like the other ones, like the other ones, other parts? I see, I see. Okay, so for the first one here, we have a carbonyl, right? And we're used to protonating that with some kind of acid like H2SO4 or H2O plus, but we don't have that here. We have HCl. So that's our proton source. That carbon oxygen here is going to get protonated by the HCl, and then that activates that carbonyl there. Once we have this right here, whenever you see a potassium K or Na there, that's always a positive charge. Whatever is attached to that K is negatively charged. So this Cn here is our negative charged nucleophile, where that negative charged nucleophile attacks that carbonyl carbon and pops the double bond onto the oxygen there, right? And then when that happens, we get this final answer here, right? When you see a carbon attached to an alcohol and a nitrile group, this is called a cyanohydrin, right? It's very similar as what we have been doing like earlier, but instead of H2SO4, we have HCl. Instead of alcohol, we have Cn minus, right?
He's a guess that one.
Oh, you guessed this one?
Yeah, just
Oh yeah, that's right, that's right. Nice. Do you want to try which part do you want to try?
try only try the NH2 one from 4 and 5.
4 and 5. Okay. Let's see. Let's do 5. 5 is the harder one. Here. You wanted to try writing it up on the board here? Yeah. And then you could like scroll down as well. Have you been able to try this?
Yeah.
Oh, nice, yeah. All right. Can I check the other one? So, hydrogen, nice. This one forms an acetal, where the R is H3, nice. Right, so this one here, right? We have catalytic H2SO4, and you want to just think of that as a solvent because we have alcohol as well. When we protonate this carbonyl oxygen, you know how some kind of alcohol attacks? The alcohol here is that structure there, where this is going to be an intramolecular reaction.
Oh, right.
Right, it's going to form a ring, like a let's see, 1 is the oxygen, 2, 3, 4, 5, 6-member ring, where one of the atoms in the 6-member ring is the oxygen there. And then let's go to the next. This is the enamine, that's correct, because we have a secondary. But if we have a primary amine or ammonia, it should be enamine. Yeah, the difference between enamine and enamine, right? Which is yeah. Oh, this should be an enamine. This right now is enamine.
Oh.
Yeah. They sound the same, like enamine. Enamine, yeah, with the I.
So the I.
Yeah, which is like carbon, double bond. Yes. Yeah, that's right. Since we have this secondary amine here, our product will be this enamine, where the NR2 is that NR2 right there, and we have an alkene right next to it, right? That is different from part D because part D does not have a secondary amine, it has a primary amine. And when we have a primary amine, that's going to form an enamine. I mean an imine with the I. Primary amine, product, imine with the I, which is a carbon double bonded to a nitrogen. And that nitrogen there is going to be bonded to this R group here, CH2, CH3, like that. Right. No more hydrogens. Nice. Okay. Okay, let's look at the intramolecular ones and go over that mechanism for the intramolecular ones. Let's look at C. Okay. So we have a strong acid, H2SO4, which is going to activate and protonate the carbonyl oxygen here. When that happens, this activated carbonyl is a strong nucleophile now. What is the nucleophile is going to be this alcohol here within the same structure molecule as the electrophile. So this right here is going to be an intramolecular reaction. And all intramolecular reactions always forms a ring in the product, right? We know that this oxygen here with a pair of electrons is going to attack that carbonyl carbon and pop the double bonds to oxygen right there. That will form our 1, 2, 3, 4, 5, 6-membered ring. Start the atom at the attacking atom. Start the number at the attacking atom, which is this oxygen here. End the numbering system at the atom being attacked, which is that carbon right there, right? Where we know the 6-membered ring has an oxygen in it. So let's say that's 1, 2, 3, 4, 5, 6, right? Oxygen still has a hydrogen, which it makes that give a positive charge. Carbon 2 has a methyl. Carbon 6 has an OH and a methyl group there, right? Where the very last step here is to neutralize this positively charged oxygen by deprotonating it, right? And give us this neutral product here, right? And do you guys know the name of this product? Is this an acetal or hemiacetal? Hemiacetal, right? Because this carbon here has an OR group, which is this OR group here, and an OH group, which is that OH group there. Hemiacetal. Nice. Okay. Yeah. Keep this in mind because right now, 118C students are coming back to this concept. Like at this point in the quarter, they're going back to hemiacetal and acetals. Right? Yeah, it does an intramolecular reaction by having this nucleophile here, which has a pair of electrons, attacking this activated electrophile there.
Oh, okay.
Right. So when that happens, it wraps around and closes the ring. That atom 1 makes a new bond with atom 6. That's the new bond right there that gets formed.
What is the H2O in this case?
Oh, right. The H2O here, if that wasn't there, the H2O would have attacked this electrophile instead, right? But that's an intermolecular reaction where the nucleophile is separate than the electrophile. But intramolecular reactions are faster than intermolecular reactions, right? So we prefer intramolecular reactions over intermolecular reactions.
So the H2O there just like mix.
Solve it.
Oh, okay.
Yeah, it will do nothing.
Okay.
Yeah. Like, I think it's just there to hold the acid in place or something. No problem. See ya. Yeah. And that's it. Any other questions?
Oh, could you do number 2?
Yeah, number 2. Let's see. Right. So for this number 2, B, this one. Right. So for this one here, we have a carbonyl, specifically an aldehyde, and two alcohols, an acid catalyst. That acid catalyst is going to protonate and activate the carbonyl and make it a better electrophile. Now, because it is a better electrophile, this weak nucleophile alcohol can attack that carbon-carbon, pop the double bond to the oxygen, and give us this tetrahedral intermediate, where we protonate the group we want to leave, deprotonate the group we want to stay. We want to keep this OCH3 group, so we're going to deprotonate that group using the conjugate base, HSO4 minus. And I'm going to now leave the hydrogen invisible, like that. Now we end here with the hemiacetal if we had one equivalence, but we have two equivalents, so we're going to go all the way down to an acetal. We want this OH group to leave, so we have to make that into a good leaving group by protonating it with a strong acid. Once we protonate that with a strong acid, we get a good leaving group, where to drive that good leaving group off, we have to form a carbonyl there and then kick that good leaving group off like that, right? That will form this carbonyl that's activated right there. And I redrew the hydrogen there because it was always there, right? Now I bring in the second equivalence of the alcohol, which is going to attack that activated carbonyl, pop the double bond onto the oxygen, and give us this OH3. Now I'm going to leave the hydrogen invisible again with this OH3, which that oxygen still has a positive charge because it still has a hydrogen, where the final step is to neutralize the positive charge oxygen by deprotonating it with the conjugate base and reforming our acid catalyst. And now this right here, is this a hemiacetal or an acetal? Acetal, right? Because this carbon here has two OR groups, OR, OR, acetal. Nice. We stop here because we had two equivalents. If you don't have two equivalents on the arrow, but you just have the alcohol, assume excess. But if you see one equivalence explicitly, then you would have to stop at this hemiacetal if you see one EQ. Nice. I can't.